RDCSEA International. With a career spanning over 30 years, Mr. Cole began his journey in ocean science back in 1978 at the Florida Institute of Technology. Since then, he has contributed significantly to global oceanographic research, working closely with prestigious institutions such as NOAA, NSF, and the Pacific Marine Environmental Laboratory. He has a vital part of major international programs, including the TAO and Territon Array, TOGA, TOGA4, and the Pan American Climatic Study. As a co founder of the University of South Florida's Ocean Circulation Group, he played a pivotal role in expanding research efforts across the Pacific, Atlantic, Gulf of Mexico, and Caribbean. Mr. Cole brings extensive expertise in oceanographic measurements, ADCP deployments, and biotechnology. Even in retirement from USF, he remains deeply engaged with the oceanographic community, contributing through RDSEA International and participating in global initiatives such as RAMA under the Indian Ocean Observing System. He is also an active member of key organizations, including the Marine Technology Society, Data by Cooperation Panel, and the Tropical Mood by Implementation Panel. Mr. Cole, it is a truly our honor to have you with us today. We look forward to the great enthusiasm, to the knowledge and insights you will be sharing. Please joining in Please join me in welcoming Mr. Richard Cole. Thank you. I welcome.
Thank you. Thank you. That's quite the introduction. Good morning. It's a pleasure and an honor to be here, standing in front of you and talking about my life's passion, and that happens to be ocean observing. I've been doing it for a very long time. We're going to talk about CWIRD. CWIRD is our acronym for Coastal Warning Rapid Response Data Density. We've broken all rules by creating an acronym that long. Usually acronyms are only 4 to 6 characters, but it's okay. It's our acronym and we like it. So we're going to get to the coastal ocean in a few minutes, but what I've done here is built a timeline on how coastal ocean observing actually started, at least in the United States. And coastal ocean observing is a derivative of what we did and continue to do today in the deep ocean. So we'll get to CWIRD in a few minutes, but first, a little bit of history about myself and how did a kid from Western Pennsylvania, Pittsburgh, growing up on the shores of the Ohio River, end up in Chennai, India, talking to all of you about ocean observing. So we'll touch base a little bit on that as we move forward. So a little bit of a track of our discussion. We're going to go through a little bit of history, get to coastal monitoring, the present systems. I use Florida. That's where I live and that's where I'm from. I use Florida as an example because there is a lot going on in the Florida coastal regions. Not enough, because as we talked about yesterday, there's a lot of data lacking in the coastline of the United States. We're hoping to change that with the CWIRD system. We'll go through CWIRD. We'll talk about the gaps of monitoring in the state of Florida, coastal waters, and then we'll close in closing. So I got my first at-sea experience in the United States Navy. I was stationed aboard 2 aircraft carriers. This is the USS Constellation, my first ship, and my second ship was the Saratoga. I learned just about everything a human being needs to know to get through life on the USS Constellation, and that happened overnight. It happened very quickly. There's 5,000 people stationed on aircraft carriers. As an 18-year-old kid, being thrown into that mix was quite an experience. It was actually amazing, and it set the tone for what I'm about to show you. My academic experience, when I got out of the Navy, I used the GI Bill, and I chose Florida Institute of Technology. They have an amazing program in oceanography and ocean engineering, and I thought it was a great place to get that experience. Some call it FIT, the other MIT. This was an amazing experience as well. And again, it contributed to setting the tone from where we're going to show you. My goal, once I found out about the National Oceanic and Atmospheric Administration, NOAA, my goal was to get in with NOAA and learn as much as I could. It also allowed me to meet a lot of different individuals throughout the oceanographic community, especially academics. So my first ship was the Rainier. It was a hydrographic surveying ship. It's still working today. They sent me to Hawaii and then to Alaska, two of my most favorite places on Earth. And then my second ship was the Discoverer, one of two global oceanographic research vessels that NOAA offers. These ships have been retired. The Oceanographer and the Discoverer are now retired. They're building two new ones. But with what's going on with our politics in the U.S., we don't know what's going to happen with those ships. It's going to be very interesting to see. Um, and that led, once when I was on the Discoverer, I met the crew from Pacific Marine Environmental Lab in Seattle. And the next thing I knew, I was offered a job at the lab. And I spent most of the 1980s at this lab. And that's where I started to learn about ocean observing in the Pacific. So this, I'm sure many of you are familiar. I know you're familiar with Rama in the Indian Ocean, but it all started in the Pacific with what we called EPOCS, the Equatorial Pacific Ocean Climate Study. And that is this array right here. When I was at the lab, there was only 7 or 8 systems in the water. My lab's crews, research crews, as a federally installed sites 12 through 17 in the Eastern Pacific. And that obviously that has led to a monitoring array in all 3 oceans, known as the Global Tropical Mooring Array. This is the NOAA ship Kaimi Moana, Ocean Searcher. These were donated to the NOAA from the Navy. They were built to seek out submarines. They were very quiet in the water, and the quarters just to live aboard were very, very comfortable because these ships usually were working in the North Atlantic, chasing Russian submarines. That led to the University of South Florida. I did a cruise with their group. They put the very first 80 on the equator at 0 degrees, 170 west. That was the first ADCP. If you're not familiar with ADCPs, it's acoustic Doppler current profiler. So we measure the current velocity and direction using sound. We'll talk a little bit more about that in a few minutes. And that led to, we developed a group called the Ocean Circulation Group under the direction of Robert Weisberg. With Bob Weisberg, myself, our data manager, and one graduate student in 1989. And that grew into a very large group you'll see in a couple of minutes. And then, so RDC, when we were developing the first coastal monitoring program in the United States, nobody else was doing it. I started to get a lot of phone calls from other regions of the nation who wanted to do the same thing. And after a while, I said, I could probably start a consulting business with all these phone calls. And that's how RDC was formed 23 years ago. Again, so because of my experience in deep water, I was getting a lot of phone calls from other groups. And I got a call from Circulation Group under the direction of Russ Weisberg. There we go. With Bob Weisberg, myself. This is the University of Sao Paulo in Brazil. And they are working with the United States and France on the Parada program in the Atlantic. And they wanted to make their own systems. NOAA was providing all of these systems for this program, as well as the Muslims in France. They wanted to build their own. We ended up building one and deployed it in the Western Atlantic. And then I got a call from the first Institute of Oceanography in China, in Qingdao. And this was Wei Donghu, who was a good friend of Benkett's. And we mirrored the TAL systems in the deep water, and we deployed that on the Llama program. And then we got another call from the Ocean University, also in Qingdao, and they wanted to start deploying their own systems in the Western Pacific for monitoring the monsoons that have a huge effect on the Chinese continent. And this is our buoy system at the surface, and so this is the Atlas system that was developed at TMEL. Atlas stands for Temperature Line Acquisition System. And what we wanted to do was mirror everything that this system does with off-the-shelf equipment. Basically, you can purchase from all of our instrumentation manufacturers, and we were able to do that. It was very successful. This is an updated TAO system, but it's on the Rama program. This is just due south of you here in Chennai at 0 degrees, just a couple of days steam from Jakarta. And we also do a lot of subsurface mooring work with ADCPs. This is in the Gulf of Mexico. I'm going to show you some data from this site in a few minutes. So you have to understand that to get to coastal monitoring, we pretty much use all the same sensors that we use in deep water on the coast. Just less sensors on the mooring because the moorings are much shallower. This is the Atlas system that was developed at TMEL. Okay, so let's move to the coastline. This is our group at USF. That's Bob Weisberg on the right. The group has grown over the years. There's a lot of different graduates. It was good to hear Jyotika Brahmani's name. The previous speaker mentioned Jyotika got her PhD in our group under Bob, and she's now head of Schmidt Institute of Oceanography. She wasn't here the day of this picture, but it would have been nice to have her. And those are some of the ADCPs, different frequencies that we use. And this is a CTD. CTD stands for conductivity, temperature, and depth, pressure sensor. Those are the basic measurements that we use in physical oceanography: current, speed, direction, and density. So we, as a group, the group that you just saw, we had a lot of equipment sitting on the bench because we would deploy in the Pacific, and that gear would stay in the water for 12 months, maybe even longer. So we had a lot of gear in the lab that was just sitting there on the benches, and we decided, well, let's start making measurements offshore in the Gulf of Mexico. And these are a variety of different programs. These are bottom-mounted ADCPs. We didn't start surface moorings until the U.S. Geological Survey had just moved from Woods Hole Oceanographic up to Cape Cod. They had just moved to St. Petersburg, Florida, and they knew we had this gear, and they wanted to start making measurements, velocity measurements offshore. They were a coastal studies group, and they were very interested in sediment transport. So we went to the National Data Buoy Center in Stennis, Mississippi, and we came back with the design of this mooring. We were very confident and very good at working in 5,000 meters of water, but we knew nothing about 50 meters of water. It's a completely different animal, a totally different environment. So we came back with this design that is still used today. And ultimately, this was what we called the ENC array. It was the very first coastal monitoring array in the United States. ENC it was 3 different funding agencies. E was for EcoHab, which was a NOAA Red Tide program. The N was for the Navy, which was Office of Naval Research. It's a civilian arm of the U.S. Navy that funds oceanographic research. And then the C is for COPS, which was state-funded Coastal Ocean Monitoring Prediction System, which still exists today. This is just kind of a timeline of the buoy designs. Here's our first system, 1993. We designed it in 1992 with basically just an ADCP looking down, not in real time. We had to recover and download the data. Then we added 3 seabird CCATs on the mooring to get density. Then in 95, we added meteorology at the surface. Now we're getting the full mid-ocean component of the ocean. And then we went real time in '98 with transmitters using NOAA's GOES. It's a geostationary satellites, polar orbiting. And then today, this is the system that's still being used today. These are seabird microcats, and they are in what we call inductively coupled. So we use the process of induction to transmit the data through the mooring cable to the buoy. It's actually brilliant. It's actually 1850s technology. I think the developer's name was Faraday, using the process of induction, and that's used on most of the systems in the water today. Okay. And then the C is for COMPS, which was state funded coastal ocean monitoring prediction system, which still exists today. This is just kind of a timeline of the buoy designs. Here's our first system, 1993. We designed it in 1992 with basically just an ADCP looking down, not in real time. We had to recover and download the data. Then we added 3 seacats, seabird seacats on the mooring to get density. Then in '95 we added. Okay, so again, that's the system that we developed at USF. It's still in use today, and of the ocean. And then we went real time in '98 with transmitters. This was the full monitoring system in the state of Florida between the Gulf of Mexico and the Atlantic coast. This is a combination of University of South Florida mooring systems, coastal monitoring stations that included tide gauges, meteorology. The blue dots are NOAA's National Weather Service buoys that monitor the sea surface, wind speed, direction, relative humidity, barometric pressure, and sea surface temperature. This has been completely diminished due to the lack of funding over the years, as you're about to see. So here we are today in the state of Florida, and that's used on most of the systems in the water today. This is what's left of that COMPS system developed by the University of South Florida. It's got 4 buoys in the southern Gulf, and the green dots are coastal stations, again, tide gauges and meteorology. Again, there's so many gaps in data, and we talked about starvation of data yesterday, and we definitely have a starvation of data in the state of Florida. And so our definition of metocean includes the water column. The water column has been left out of the equation for about the last decade. NOAA made a shift about 10, 12 years ago to focus mostly on the sea surface. And that's largely driven because there's a lot of satellites in the sky that will determine the sea surface temperature of the oceans. And it's inexpensive using the satellite data. It's expensive to send us to sea with ships and day rates and whatnot. So then that's become a problem, as you're about to see. So here are the 3 components of the monitoring systems in the state. USF's COMPS program. Mooring systems, coastal monitoring stations that included tide gauges. So this is NOAA's National Data Buoy Center, National Weather Service moorings. 2 on the East Coast and 5 in the Gulf of Mexico. Again, they're only monitoring the sea surface, and that's a serious problem, especially when it comes to hurricane tracking. These are wave buoys. This is a program funded by the U.S. Army Corps of Engineers. It's headquartered at Scripps Institute of Oceanography in San Diego. They're basically spherical buoys made in the Netherlands by a company called Datawell, and they measure height, speed, frequency, and direction of the waves. The Army Corps is responsible for our ports and harbors, monitoring our ports and harbors of many different variables. They use these wave data as a calibration system. Okay, so let's move on to CWIRD. Again, CWIRD is our acronym for Coastal Warning and Rapid Response Data Density. And at the end of the day, we are planning on engaging AI into these data sets. It's myself, Scott Duncan, runs a company called NavOcean. They're from Seattle, Washington, and also Portland, Maine. and they make a small automated surface vehicle that sails and collects a lot of data at the surface. Tim Mulvaney sits in London. He's our AI, machine learning, deep learning expert. He's a coastal engineer, and he has a lot of experience using AI, and we're hoping to marry that knowledge with our knowledge of collecting data. So this was last summer, and this is the problem. This was last summer. This is in front of my house. I had 4 feet of water in my house after Hurricane Helene had come through, and we lost just about everything. You can see it's all out on the front street. And then a week or so after Hurricane Milton came through. The problem that we're having is that there's no water column data being collected in the shallow waters of the West Florida Shelf. The West Florida Shelf spans from the Mississippi River all the way to the Florida Keys. It's the broadest continental shelf on Earth. It's very shallow and it's very warm. We're experiencing above average temperatures as of last month. We've already had 2 disturbances of storm formation, one in the Atlantic and one in the Gulf. And that's a little early for that to happen. And we've also had a red tide boom too, a little early. So this is the problem that we're trying to fix with Seaward so that we can get coastal water column data to NOAA, to the modelers, to better forecast and track storms. So here's data from that CDIP program, the waves, those red dots that I showed you. When Helene was due west of Tampa Bay, I put that wave buoy in 2008. It was the first one in the state. We put it in with the university. When that storm passed almost 200 miles west, the maximum wave height reported on that buoy was 62 feet. That's almost 19 meters. That's unbelievable. There were 30-foot waves hitting the beach. I saw some video from people who had cameras on their condominiums. There was 30-foot waves hitting the beach. It was just amazing. And the storm was 200 miles away. We've never seen that before. And then 10 days later, Milton came through, and the maximum wave height for Milton, which turned south of the bay, it was forecast to hit Tampa Bay, but it turned at the spur of a moment. It made a 90-degree turn, and it hit Sarasota and Fort Myers, which is right here. And the problem there is those folks did not evacuate because they were told the storm was going to hit Tampa. And this is part of the problem. The storms are outsmarting the modelers because they don't have the proper data to input into the models. Here's just an example of what's happening. These are 2 storms over the past couple of years, Otis and Ian. Ian was an amazing storm. It had a 22-foot storm surge on the beach when it hit. And again, we were told that Ian was going to come and hit Tampa Bay, but it didn't. It turned south of the bay. And you'll notice this dark red color. That's the storm rapidly intensifying to a Cat 5. A Category 5 hurricane begins at 157 miles per hour wind. We've not seen this over the years. The storms are coming more frequently than they used to, and they're increasing in speed as they get closer to the beach because it's shallow and waters are very warm. And here's the problem. You can see the far right graphic. This white space here is no data. There's no data in that area, and that's a serious problem. There's a lot of data out here in the deep water through the Argo program that monitors CTV data and sends it back in real time and satellite. But there's nothing along the coast anymore. USF had moorings that were sending back conductivity and temperature in real time, but with the decrease in funding, that all seemed to go away. So Seaward hopes to rectify this problem and add this coastal data over time. So this is our system. We've got a surface mooring that's going to supply fixed long-term time series of all mid-ocean parameters. And we can even, what's becoming more popular in Florida is water quality because of all the red tide that's happened. The red tide is a dinoflagellate that blooms at depth. I think that it's called Carinia brevis. It blooms at depth, and then upwelling brings it to the surface, and then the winds push it south, and it causes a lot of issues, especially for the tourism industry in Florida, because you can't get in the water, you can't go to the beaches. I swim every day, and in 2018, I swam in the Gulf 2 times. I was lucky. And then we're using Nav Ocean Nav 2, a Nav Ocean Nav 2 ASB that will have the same sensors that the buoy has. And then also Heffring Engineering is in Boston. They're a spinoff from Nortec ADCPs, and we're going to use their glider for subsurface work. And so here we get in a little bit into the hurricane situation in the southeast of the United States, not just Florida, it's also Georgia and the Carolinas. They get hit, the whole Gulf Coast gets hit with hurricanes later in the summer. They seem to form off of Mexico, off of the Yucatan Peninsula in September and October, and they come due north into the Gulf Coast. And they're causing a lot of damage. We don't have 2024 up there, but Helene and Milton cost billions and billions of dollars after it was all said and done. Again, here you can see the increase in the first Cat 5 we saw was back in 1930, and you can see that they're increased over the time frame up to 2020. That's when this graph ends. But we're seeing more and more high speed hurricanes develop in the summer months. Oh, so Florida also has a serious problem with sea level rise, especially in Miami. Florida's basically it's just basically a large coral reef that's exposed, and the salt water from the Atlantic, especially in Miami, gets underneath that bedrock and floods the city sewer systems. And this is becoming more and more of a problem. And it's supposed to sea level rise is going to increase as time moves forward. Again, we talked about it yesterday. There are new players in the ocean data game. It's not just for the federal government or the academics anymore. There are other industries that want to know what is happening in our local oceans. That would be the insurance industry and the financial markets. They want a better prediction than they're getting today. And the insurance industry, again, I live on the beach. Insurance is not cheap. And if you can even get it today, a lot of insurance companies are pulling out of Florida because they don't want to pay out all the damage that they have to do after these hurricanes come through. So the CME, which is the Chicago Mercantile Exchange, that was developed back in the late 1800s. And what the CME does is they monitor the financial markets, and they're now requiring that in the stock exchange needs to pay attention to climate, to the ocean climate, and what's happening with it as they move forward. Okay, so here we go. Seaward. These are some in the field pictures of our three tools: the NAV2 buoy, the glider, and then what we did with what RDC did with the comps buoy from USF is we compressed it because we knew we were going to be going. Let me back up. Back in after the 2008 2009 economic downturn, the new motto within the ocean observing community was we want the same data, but we want it to be cheaper. So we needed to be able to supply the same data that we were supplying, but we needed to do it in a less expensive manner. So we downsized the buoy, the USF buoy, to what you see here. And again, here's our three tools in the water with transmitting data back in real time. Again, the sensor choice, we can choose the sensors per project as what's needed, but we want to make sure we have the basic Met-Ocean parameters covered. Here's our full up USF Met-Ocean buoy system. This is just west of Tampa Bay, C12. It's in 50 meters of water. It's been in place now since 1994, I believe. And then here's the compressed version of that buoy. This is in Costa Rica. This was monitoring. They were building a new container port on the Costa Rica, on the Caribbean side of Costa Rica, and there's a lot of coral reef in the region. So the job of this buoy was to monitor the turbidity and the current speed. If the currents exceeded 1 knot, they had to stop dredging where they were working because they didn't want the sediments to cover the coral reef. And Costa Rica is very environmental and don't do anything to their turtles. If you do anything to their turtles, you're going to end up probably in jail. So here's an example of a data stream. You can see here, this is the wind speed, which is completely opposite of the currents. This is the currents at 2 meters, 7 meters, and 12 meters. This was deployed at the mouth of a river, so we had freshwater intrusion coming from this river, which had a high rate of current. And then here you can see the differences in the wind and the current. That's just an example of how we look at this data. So we're working with companies to develop new technologies. DOT, Dartmouth Ocean Technologies out of Canada, Halifax, they manufacture an eDNA sampler. eDNA has entered our world, especially for harmful algae blooms. And the idea here is we will deploy this sensor on the buoy, and we will know when the last sample was taken. There's nine filters in a cartridge, and somebody will be able to go out offshore and change out that cartridge, bring the samples back, and then process them in the lab. This is the crawler. This was developed at the NOAA lab, PMEL. McLean is here. They have a booth out in the hallway. So the crawler will replace all of the CTDs on a mooring line with one CTD. And it uses wave action. Oh, this video will play. No. The wave action that moves the buoy will ratchet the trawler up the mooring line, and then the cams will release, and it will free fall to the bottom, collecting conductivity, temperature, and depth, and whatever other sensors we decide to put on the crawler. And then it will ratchet itself back up through the wave action of the buoy. It's actually brilliant. One CTD, one calibration versus multiple CTDs is a much better approach. So this was developed for TAO, for the Pacific, but we're hoping to use it in the shallow waters of the coast. Oh, there we go. So that you get an idea of how it works. This was monitoring. They were building a new container port on the Costa Rica. There's a program out of Woods Hole funded by the National Science Foundation called the Ocean Observatories Initiative. They're deploying the trawler in 30 meters of water, and they're getting very, very good data. So we have high hopes to use the trawler. This is our Rama buoy. We're also working with Pro Oceanus. They're also out of Halifax with a CO2 system. We want to put CO2 monitoring on all seaward buoys. This sensor will give us the partial pressures of CO2 in the water, and then there's a pump on the surface that gives us the partial pressure of CO2 at the sea surface, so we get both in water and in atmosphere measurements. This was the first CO2 sensor on the Rama program. It's very successful until the fishermen hit the buoy and did a lot of damage. That's a problem as well. Here you can see the differences in the wind and the current. That's just an example of. Okay, tab 2. You can see how easy this is to deploy. I have a video. Hopefully that will work. This was developed by Scott Duncan from NavOcean, and they've been using it on a variety of different projects in the state of Florida with the Department of Environmental Protection. Here's the specifics. We can outfit the boat with whatever sensor we need for whatever the project requires. It's small. We will probably have to make the boat a little bit bigger in the future because we want to add a profiling CTD. There is a CTD on the market that's very small, called the Castaway, and we will mount a small winch and we'll be able to stop the boat and deploy the CTD, get a profile, recover, and then the boat will move on to the next site. That's in the plans. I don't know if this will. Here we go. This is a long video. I'm just going to show you a few minutes of it. You can see how easy it is to deploy. Nav Ocean's been in Florida on a couple projects in the Lake Okeechobee. Lake Okeechobee is on the east coast of Florida. It's fresh water, and it has a lot of issues during the summer when the water gets warm and we get a lot of rain. So the data goes back to a portal back on the beach. So here's Lake Okeechobee. You can see this is blue-green algae. It develops in the summer, and it's mostly caused by the agricultural community with fertilizers. There's a lot of sugar cane. There's a lot of other products, citrus products around the lake, and the fertilizers from those farms end up in the lake, and then these blooms happen. So Scott and Nav Ocean were hired by the Department of Environmental Protection to monitor this blue-green algae. The problem with what happened in 2018, we had a huge red tide bloom off of Tampa Bay. When we get a lot of rain, the Army Corps, the lake floods, the Army Corps opens the gates and lets they drain the lake. The water goes into the Atlantic and it goes into the Gulf of Mexico. Well, so does the blue-green algae. And the number one food product for Corynea brevis is blue-green algae. And that bloom in 2018 just exploded. It was a disaster. And then all of a sudden, money was falling out of the skies from Tallahassee to go and study it. $100 million. And it went to USF. It was very crazy. But Scott, they were very successful at monitoring the whole lake with the NAV too. Here again, it's just another slide of showing some data. This is up in New England offshore. Okay, our glider, Ocean Scout. So Heffring is a spin-off from Nortec. ADCPs are out of Norway, but they're headquartered in Boston. It's a very dependable glider. It's very easy to program. It's very easy to deploy. We're hoping to get some good data using this system. Here's the internal parts. It uses an oil bladder for propulsion. There's no motor to move it. It basically, you program it to do a specific grid, and it does a fantastic job. Here's the specifics. There again, so here's a deployment and some data from the glider. I visited Heffring last November when we introduced Seaward at Harvard's Green AI meeting, and we introduced the Seaward idea using AI at that meeting. Should work. CTD on the market that's very small, called the Castaway, and we will now there we go. So you can see how easy this is to deploy one person. Get a profile. I believe this is off of Hawaii. On to the next site. That's in the plans. And off she goes. So the ultimate goal with the NAV2 and the glider is we're working with DBV Technologies out of Rhode Island. Bud Vincent is a retired Navy commander, and he was faculty at URI. He's developed a very small, low-power acoustic modem. So the idea is to have a receiving modem on the NAV2, a transmit modem on the glider, and the glider will basically follow the NAV2 and transmit its data without having to service. That's the ultimate goal, and then we can do a lot with this system moving forward along with the buoy. So yeah, right data enhances disaster response. So we're going to take a look at a little bit of data. We need more data. We have to have more water column data especially for the changing climate and all the storms that are hitting us. So here's a look at a transmit from the Rama buoy on the equator. So we have a couple of different schedules. We have a 10-minute schedule, a 1 hour schedule, a 3 hour schedule, and there's different things happening within those schedules. But what we transmit is the 1 hour schedule. So the transmission, oh, there we go. So we transmit a timestamp, date and time, and then that's your whole met string, including meteorology, relative humidity, barometric pressure, solar radiation, downward sunlight, reflected sunlight. Uh, uh, we can get rain. We can put a rain gauge on board. We can get millimeters per hour, and then we'll this is our CTD. So there's 13 CTDs here on the mooring, transmitting in real time, inductively up to the buoy, and then back to the lab. Here's our CO2. Our CO2 measurement came in every 3 hours. And along with that hourly schedule, these are 4 single point ADCPs on the mooring. So the ADCP data is collected in binary format. You can't transmit that. It's too much. It's too big of a file. So what we do is we convert it on the buoy. We convert it to hex ASCII, and then we can transmit. And then once that transmission hits the server back at the lab, we can either convert it back to binary and run it through manufacturer provided software to print out graphics, or just take the hex ASCII data and send that over to a MATLAB program and we spit out graphics. This is an example. That subsurface mooring I showed you earlier was deployed in 80 meters of water just west of Key West back in 2004. That system got stuck for 2 years. We couldn't get. We tried to get to it. The weather was too bad. The ship broke. We were using. The ship had to go into dry dock for almost a year. So we did not get to this system for 24 months. And the good thing was it was full of data, and it measured a lot of different hurricanes that passed over it. Specifically, Hurricane Katrina. I'm sure you heard about Katrina back in the day. It did a lot of damage to Louisiana, New Orleans, and the whole northern Gulf Coast, as you can see here. So this is U and V. U is north. This is east. Anything else would be south, west. But you can see here all of the flow with. Whoops. The ultimate goal with the NAV2 and the glider is we're working with TPV Technologies out of Rhode Island. Maybe I can do a dance for you. Bud Benson, he's a retired Navy commander, and he was faculty at URI. He's developed a very small, here we go, power acoustic modem. So the idea is to have a okay, yeah. So on the NAV2, we were very fortunate that this site got stuck, so we were able to record a massive amount of hurricane activity in the Gulf of Mexico, especially Katrina as it came across. When Katrina came across the southern peninsula, it hit Florida at a Cat 3, which is 120 miles per hour. The Gulf of Mexico was the warmest it had been in over 100 years. When Katrina hit the Gulf of Mexico, it was like an atomic bomb that exploded. It went to a Cat 5 in a matter of hours. It was unbelievable. We need more data. We have to have more. Again, here's just a view of what our metadata looks like coming in. We get the raw data, it goes to a script, and then it spits out these types of graphs. This is the Rama buoy on the equator. This is temperature data from the Rama buoy, 700 meters. So there's 13 CTDs on the mooring line. The crawler will be able to provide this type of plotting just using one CTD. That's our goal. And you can see here it's a well-defined thermocline, which is very common in all 3 oceans, right around 100 to 120 meters. If you're a tuna fisherman, that's where you fish, right at the thermocline. That's where the tuna hang out. And this is conductivity in the upper 100 meters from that same Rama buoy. So we are talking to AI chip manufacturers. We want to embed chips into our controllers and start using AI to compress data. AI is going to be able to do a lot of things with ocean observing. So we are talking to a variety of different groups about these chips. The number one issue will be power. They're very power hungry. We're already using a lot of power with our sampling, and we normally use solar charge. So we connect the controllers to solar panels and a solar charger. So we're going to have to get through the power consumption issue. And these are some of the ideas that we have in using AI, camera, vessel identification, vessel traffic collision avoidance, marine protected areas, monitoring coral reefs, fish, dolphins and whales, monitoring birds and bats. Believe it or not, birds and bats. I had no idea that bats went offshore, but they do. They're chasing insects in the wind. And when you have to do an environmental impact study for offshore wind, you have to provide information on birds and bats in with your oceanographic studies. And then again, compressing data sets, rapid response navigation. If the buoy determines that there's a harmful algal bloom in ongoing, the buoy can reach out to the nav2, and the nav2 can talk to the glider, and they can divert and go and monitor that bloom. We're hoping that the AI will be able to help us with that. And again, this is some of Tim's plan using AI and within the system. Data sources will combine, Seaward will combine the existing data systems that are in place, NOAA, and other sources of data. The whole idea is to enhance the existing models and to create new and better models. Again, we have people on board the team. It's not just the three of us. There's a whole realm of other individuals that are on board to help us to get Seaward in place. And this is our ultimate plan for Florida. We would like to get 5 lines in place. We're hoping to get 1 to 2 this summer. It's all about funding, right? Everything's about funding. And this would be a good proof of concept of the system. So each line would have 2 surface buoys, 2 surface vehicles, and 2 gliders working in tandem. That's the ultimate goal, and we sure hope that we can achieve that. If the state of Florida were to fund an observing system, they used to, they don't anymore. This is what it would look like. This is what we would like to see with a seaward system, and even deepwater ADCPs off the shelf. You can see here how broad the West Florida shelf is. It goes all the way up to Mississippi. Over here is the Mississippi Delta. But we would like to have these systems in place in conjunction with what's already in place. These are the gap filling sites that Socorro, the southeastern domain of the U.S. Integrated Ocean Observing System, Socorro had designated 16 different gap regions between Florida and the Carolinas, and 13 of those sites were in the inshore waters. And again, we have a serious problem with harmful algal blooms. We would have a focus on these sites here with water quality. And then Seabird has a plan to go global. We would love to help you here in India, in the Bay of Bengal, or wherever. But we do see this as a global initiative. And I think my next slide. Yeah, so Seabird's equipped. It's better equipped for hurricane tracking data. That's the ultimate goal. And before I quit, before I'm done, I want to take a minute and honor our dear friend Vimbu Subramanian. Some of you maybe know Vimbu. Vimbu was like a brother to me. He passed away in 2017, getting emotional. Vimbu was our data manager at USF. He was an amazing human being. Becky knows him well. He helped start the MTS India section back in, I think it went 2015. Yeah, so Vimbu was an amazing man. He was the associate director of the USI's region Sephora in the southeast. He was here uh, looking after his parents when you were working with him. And he passed away of a heart attack in 2017. Bimbu always told us to dream big. That was his motto. And that's what Seaward is. It's a big dream. We hope to make it happen. And I would like to also thank Venkat and Preetha and all the committee who put this meeting together. That's Venkat and I in San Diego just a few years ago at the Data Buoy corporate panel meeting. I've known Venkat for a long time now. It's been a lot of fun, and I really appreciate being invited to this meeting and being able to show you what we do and our passion. And and I thank you. And I'll leave you with our contact information, and we will make a promise to you. This is our promise that we promise not to let the machines take over. Okay. No Skynet. Thank you very much.
Thank you so much, sir. We request Dr. R. Venkateshan to felicitate the moment to Dr. Richard Ko. We also request Dr. Mr. Arun Guthai to come on the stage and felicitate Richard Ko. Now request Miss S. Sujata to introduce Dr. Bala Nagajyoti.
Behalf of Department of Electrical and Electronics Engineering, SRM Institute of Science and Technology, it is our great pleasure to introduce our distinguished speaker for today's session. It is with immense gratitude we welcome Dr. Balanaga Jyoti. She received her BTech degree in Electronics and Communication Engineering from Sri Venkateshwara University in 2003 and PhD degree in ML and DL aided guidance techniques for AUV homing applications in subsea at Indian Institute of Information Technology, Sri City. Dr. Balanaga Jyoti, member of IEEE, has worked for geostationary diurnal operations in ISRO, MCF, and got specialized in attitude on orbit control systems of geostationary satellites. Following that, she has worked in cryo control system in cryo gas stage servicing facilities at SDSC Sahar and got accumulated with IEC 61131 PLC language and SCADA development for cryo filling operations and worked as a network and server administrator for database protection during pre and post launch operational activities. Presently, she is working with National Institute of Ocean Technology under Ministry of Earth Science, Chennai, India, and got specialized in underwater electronic systems, navigation, positioning, and communication systems design and development of manned and unmanned vehicles. Her research interests include subsea robotics, magnetic and vision-based homing guidance techniques for AUVs. We look forward with great enthusiasm to the knowledge and insights you will be sharing, ma'am. Please joining me all to welcome Dr. Bala
He was an amazing human being. Beckett knows him well. He helped. He helped start the MTS India section back in, I think it went 2015. Yeah, so Bimbu was an amazing man. He was the associate director of the USI's region Sephora in the southeast. He was here uh, looking after his parents when you were working with him. And he passed away of a heart attack in 2017. Bimbu always told us to dream big. That was his motto. And that's what Seaward is. It's a big dream. We hope to make it happen. And I would like to also thank it.
And I would like to thank Vitation sir and Vikram madam for giving this opportunity for presenting the talk on challenges in subsea robotics. I come from the department Deep Sea Technologies in NIOT. So we are into the development of unmanned and manned submersible vehicles for deep water and shallow water.
Being invited to this
What are the challenges in subsea robotics? I am going to explain. These inputs will be really useful for the next generation. And I want attention all students. Can you please listen to me? I request to keep your phones in silent mode and laptops also to keep off for some time.
This is our
And
promise.
I think everyone is aware that our NIOT comes under Ministry of Earth Sciences, and NIOT is leveraging in blue
Thank you
economy.
very much.
And as I told,
Thank you so much, sir. We request Dr. R. Venkateshan to felicitate the moment.
many other groups working on different technologies, and you will be listening to many other talks next after me. So we have I am from this deep sea technologies group.
We also
So
request
these are all the
Mr. Arun
different
Prakash
vehicles
to come
where
on
we are
stage and
working on,
felicitate.
and we have coastal environmental engineering protection of all the coastal offshore environment. We are also having ocean electronics department where they will be developing indigenization of the sonars and other sensors. And we also work on the gas hydrates. Our group works on the gas hydrates, exploration of gas hydrates. And then we are also having the vessel management, and the important group is ocean observation system. Dr. Aditya sir will be presenting on this. And here, yesterday our secretary was telling that food, the water, and all important. So here we are generating the fresh water for the island people. And here we are also having offshore structures where the offshore platforms will be built, and analysis will be done, and inputs will be given. And we also have this marine biotechnology.
Request
So,
Miss
which
S.
are all
Sujata to
the
introduce
technologies
Dr.
which were
Bala
framed
Nandahari.
by our founder, Dr. Ravindran sir, are all leading to blue economy. So, if required, you can visit NIOT at any time and understand. Today, about the talk, need to develop underwater vehicles and what are the different types of underwater vehicles are SRM there, Institute of what Science are and all the Technology. environment challenges and key design considerations in designing these vehicles. It is our great
Uh,
pleasure to introduce
what
our
is
esteemed speaker for
challenges
today's
is
session.
environmental
It is with
challenges.
immense
When you go
gratitude
to
we
space,
welcome Dr.
pressure will be like
Balanandhan.
vacuum, it will be
He
zero.
received
But
the
when you
BTech
go in
degree in
the
Electronics
water,
and
the pressure
Communication
will be
Engineering.
more. Like every 10 meter, 1 bar pressure will increase. So we have to develop the system which
Venkateshwara
can tolerate
University
the
in
pressure.
2003
So
and
low
PhD
temperature and
degree in
humidity
ML&D
and
Engineering,
hydrostability and
Aegis
hydrodynamics and
Technical
vehicle
Center,
control, how
AEB,
to design the subsea power
certification
system
in
and
subsea
ship-based systems,
and Indian
and what
Institute
are
of
the challenges in
Information
navigation,
Technology,
positioning,
ISIS.
and communication
Dr.
systems, and
Balanandhan
what are the vision
developed
systems, and then
IEEE as
locomotion
one
vehicles,
for the
what are the
stationary
minimum input
dynamics
design inputs I'll
mission
be
operations
just
in
briefing you.
ISRO
And next, what is
ACF
the strategic
and for
requirement
specialized
where India
applications
has to
on
go
earthly
next
control systems in
for
stationary
increasing the
satellites. Following that, she
spatio-temporal
has worked in cryo
uh,
control system in cryo gas
explorations
stage
and inspections
setting
and all.
facilities at
What we can
SPC,
do for
SPSC
next for the
Center
government of
and
India,
got
I'll be
accumulated with
giving.
IEC 6
So coming to the need of the vehicles, so everyone was saying, no, like 70% of the earth is covered with ocean. So we are having many resources, and these are all to be explored, and we have to use for the common man. So for this only we should have technology, and this is our EEZ, which has increased from 2 million square kilometers to 3 million square kilometers. And to harvest these resources in deep waters, we have many technological challenges. So, considering this, our deep ocean science exploration coming first to the gas ethics.
Development of manned and unmanned vehicles. Her research interests include subsea
Here, this is the
robotics
Krishna
and
Godavari basin, where is a potential
electrification
gas hydrate
using for
resource.
AUV.
Actually, this gas hydrate
Look
is a
forward
compressed
with
methane
great
gas,
enthusiasm to your
which is
knowledge
laying at
and insights.
1,500-meter
We
depth.
will share
So we have
beautiful
to
insights.
like inspect that
Please
how
join,
much is whether
join
it
me
is viable for
with
production
Dr.
or economically it is viability, techno-economical viability studies are being done. And then coming to Arabian Sea, so many boys are there, and then here Mahanadi, Andaman gazetted sites are there. And here CAOB, this is a main site for us where it is a potential for manganese nodules. So whatever we develop, it deep water we are saying, but why we are developing 6,000-meter temperature? Because our exploration site is ends with 5,500 meters, so we are going for 6,000 meter. If you go for Mariana Trench, 11,000 meters depth. So accordingly, and we can explore only in our Indian Ocean basin, side, like Indian Ocean only. And coming to here, Rodriguez Triple Junction, this is a hydrothermal sulfide site. Recently, our AUV has been taken there, and we have captured many volcanoes. Very interesting about this site is here we can get the living beings where they can survive at 400 degrees Celsius and 4 degrees temperature. When you go in deeper water, temperature reduction also will be there. So how they are surviving? That is the question actually. And we also work for the Southern Indian Ocean and this one. And polar regions also are there. Like Arctic and all, like voice and all is deployed. And Antarctica, we have deployed our ROV, remotely operated vehicle. And we have given underwater visual images. So what are all the challenges in deep ocean? So pressure, I was telling, every 10-meter unbar pressure will increase. So up 6,000 meters, we have the challenge to design the robot which up to 600 bar. Temperature, I was explaining you that the temperature after 10,000 meter depth, 4 degrees. It will continue in the same. So low temperature is there. And communication, we cannot communicate with electromagnetic. Yesterday, many students also were telling that electromagnetic will attenuate. It cannot propagate because due to seawater conductivity. So position determination. So now wherever you are there, now you are in this conference hall also we are knowing the position where you are. Someone can track you. But in underwater it is not so. We have to depend only on acoustics. But with a very limited range and bandwidth is very less, and corrosive seawater. So continuously, if you deploy the vehicle, also your systems will be corroded. So we have to go for sacrificing anodes like that. And all. So hydrodynamics and under various sea states, vehicle hydrodynamics is very important because you are seeing the aircraft and all, how the aerofoils and all designed. Very small change, your aircraft landing will be done and liftoff will be done. But underwater vehicle, it is called as hydrodynamics. And how much trusted to be given. Closed loop control system, when you are speaking with autonomy, this hydrodynamics is very important. Then absolute darkness. So vision systems. So yesterday I heard many presentations given by students on underwater imaging. Why image enhancement required? Because low light visibility is very less. When your light also is there, artificially you are providing light. But some studies should be done to have a complete, take the image properly. Then only we can do image enhancement. So before that, what can be done? I'll be just showing. And then limitation in our still so many limitations are there. This and all we now know that what are the challenges. So coming to hydrostatic pressure, if you see, we need the pressure tight enclosures. No water entry, water ingress should be there, and power data feed through should be there. And for the low temperature, thermal design also plays very important. And dynamic environment, first we have to see the launching and recovery system. Then hydrostatic stability, we have to see whether your vehicle is neutrally stable, neutral buoyant or positive buoyant or negative buoyant. So hydrodynamic efficiency, I was telling for the closed loop control system, where you have to control roll pitch, heading, and the position, 6 degree of freedom. These hydrodynamic parameters are very important. And power delivery, on-board power supply. If it is remotely operated, it is tethered vehicle, means unlimited power will be there. But when you come to autonomous systems, like the drones where you will be changing the battery, so like that, autonomous vehicle also onboard power supply is the limitation, and we cannot increase whatever size also. Based on your endurance calculation and all energy requirements, your battery should be computed. Then the vehicle control, same thing. And salinity. So salinity is actually direct parameter of conductivity. So attenuation of radio frequency signal, because if your battery is very saline, your radio signals cannot propagate. So these navigation and communication subsystems are very challenging, and I am working on this system especially. And darkness vision system, how we have to design to get better images. Sessions I will be giving as inputs. And soft seabed. So seabed locomotion based on the seat strength only we can design. Otherwise, systems will sink and we cannot treat the vehicle. So types of underwater vehicles. Actually, we are having remotely operable vehicle and autonomous underwater vehicle and manned submersible. So these both are autonomous actually. But this will be tethered vehicle where the power and data will be transmitted through the cable, optical umbilical cable, which is of like if you are going for 6,000 meter depth, means 7,000 meter cable will be there. And this is a tether management system where 400 meter cable will be there. So you can have the survey coverage of around 400 meter of radius. But here autonomous we can go up to kilometers of for the inspection and all exploration. So if you compare this ROV, it is unlimited endurance because you will be having the power from the ship, and only after one area coverage you can go with the ship to the next area and cover. Then autonomous endurance is limited because based on the batteries on the. Then operated vehicle also it has autonomous. It is battery operated, and connectivity. I was saying this is tethered and both are untethered. And intervention capability. ROV is limited because you have to see the vision feedback and then we can do the intervention with manipulators and all. AUV, it is not so mature because autonomously vehicle has to take vehicle should be more intelligent to be an intervention operation like welding operation of the pipes and all in subsea. Here, human is in the loop, so it is very well proven. And filming Titanic and all with man submersible. First, Alvin has tried. Alvin vehicle is the first one from Woods Hole, USA. So coming to NIoT ecosystem, vehicle ecosystem, we have the first ROSA vehicle, remotely operable submersible, which is 6,000 meter depth rated, and it went up to CAOB site 5,289 in 2010 actually. I joined NIoT in 2012 only. So after I joining, we have developed this 500-meter depth rated vehicle, and this has gone more than like 40 dives. Many coral sites, biodiversity studies were done in Andaman and Nicobar, or then Mangalore, near Mangalore and all. So this is the AUV we have procured from AUV from Kongsberg. Now we are learning from this vehicle many things. This one we can say this is a marvel for ocean technology. And here we have done now 11 dives in CAOB site and hydrothermal site. Now sulfide site also is over. Human submersible, we are in progress. Actually, recently we have done wet test and we are about to go to shallow water and deep water. And this autonomous pouring system, this also, I was telling, this is for the exploration of gas layers. This is in situ soil tester. I was saying, right, to check the soil strength, whether the vehicle can crawl or vehicle can sit. So first, this vehicle will be sent and shearing strength of the soil bed will be tested, and then the next vehicle will be deployed. So this is an integrated mining system. This is actually crawler based system where nodules site it is used to pick up the nodules and pump to the shore. So coming to the challenges, so how you are designing your pressure cases? What is the formula behind that? You cannot just based on your depth rating, you have to design. Okay, so you, based on the depth, what is the pressure which will be exposed to the water? So that is the stress and all we have to take. So normally normally at 100-meter depth means it is 10 bar pressure will be exposed. So we cannot go to the acrylic pressure case and all. So aluminum pressure case, like the material also depends. But what is the thickness? Thickness also is mattering. So it will be cylindrical and covered with the circumferential hemispheres in the end. So in this way only we can design the pressure cases. So these are all the equations. So if you see our personal sphere, it will be a circular one. When you see our remotely operated vehicle, it will be like a cylindrical covered with hemispherical. So all cannot be a pressure rated systems because size increases. If you should see this is the 6,000 meter, how much is the thickness of the pressure case? So sometimes we have to reduce the vehicle weight also. So for that mechanical group is there. Actually, I am into electronics. So our group consists of mechanical engineers, electrical engineers and all. So they will be working on the structural design and using ANSYS and computation, fluid dynamics software and all. So some needs pressure compensated system also. So this is a pressure compensation where it will be filled with oil and when the pressure comes, it will be pumping and it will be releasing the oil. So this is our actually one hyperbaric test facility we have where before taking any system or design or when any system we are procuring, we are realizing we will be testing up to 600 watt. Actually, in this we can go up to 900 watt pressure, and we will test and we will qualify the system, and then only we'll integrate into our vehicle. And this is a pressure balanced oil field junction box. So some systems will be pressure rated, some systems will be pressure compensated. So some examples I wanted to give. And this is a spherical hull which is a human cabin. Why we have gone for the spherical, everyone can ask. So for uniform like a force, when it is kept in water, uniform pressure will be applied. So only it is selected in the spherical shape. So coming to the low temperature and humidity, I was telling after 1000 meter or 2000 meters, your temperature will be around 4 degrees. So when your pressure cases, everything goes into water, then outside temperature is cool. But inside our pressure cases, it is with controllers, electronics, hardware and all. So the pressure temperature difference will be there. So at the time condensation will happen. So we should have some like insulated medium where this condensation should be absorbed and your electronics should be safe. So we'll be purging with nitrogen gas. So it is an inert element, inert gas. Everyone knows that. So we'll be purging with inert gas and we can purge with helium also. But helium is little bit costly and it will be very available, less availability. Hence, we'll be purging with the nitrogen gas and we'll be putting silica gels to absorb the humidity and this condensation also uh, we will not we will not happen. And actually, we can use heat pipes also. Whatever is used now in the CPUs and all, cooling piping system and all we can use. And normally, this computational fluid dynamics will be used to optimize the thermal design. So, coming to hydrostatic stability, when you develop a vehicle, so you have to keep all the components balanced, like power, like batteries and all, we have to keep at the bottom, and vehicle should be neutral buoyant. Like coming to the Archimedes principle, if vehicle is positive buoyant, it will always try to come up. Vehicle is negative buoyant, it always sinks. So our vehicles first it will be neutral buoyant, where the center of gravity will be below the center of buoyancy. So this difference will be the delta. That also should not be more. So when the gravity point is more than the buoyancy, the vehicle will be unstable. So we'll be designing like this. So when any force is given externally also, the vehicle should come into the original shape. So in this way, you have to make the vehicle stability. A trimming polygon processor is used. I think many mechanical people will be knowing about this. So hydrodynamics and submersible control. So normally when you go in flight and all, so this drag force is everywhere. But the flight shape is in like fish shape because the drag force will be very less and the area of exposure will be less. That's why we are going into the V shape actually. So in the same way, AUV and all, if you see the area forward, like when forward motion, the area exposed to water will be very less, and hence we will be using that shape, aero shape actually. And when you go in water, this added mass also will increase because I was telling for the buoyancy purpose, we'll be adding syntactic foam, which will increase the vehicle area of the surface and then weight also. So yeah, added mass will be there and the vehicle mass also will be there. So the drag force will increase. So the thrust which you give to move forward. So these are all the parameters we have to take care. So if you come added mass and all, this is the actually Newton's laws of motion, and these are the forces required for contraction. When you want the vehicle to move in forward direction, for reverse direction, and then heading control, then these are all the rotational degrees and translational degree of motion we have to know about. This is very interesting area. Uh, in even interest also, they can contact me to work on this. So these are all the drag coefficients. This is deriving these parameters. How you will derive? We will scale down your vehicle model and then go to other facilities like IIT Madras and all. Then all the forward movements will be given. So we will be knowing all the what is the moment required, what is the force required. So we will take the parameters and then implement in our control system. So normally in our remotely operated vehicle, we will be using, since it is a man will be there, we will be controlling from the ship control console. We'll be controlling from the ship control console through a joystick. So this and all will be going to the ship, and this is a fiber optic cable, and this will be actuating the thrusters. What is your propulsion system is electrical thrusters only we are using in the remotely operated vehicle or autonomous underwater vehicle. So these are all the movement how we will capture is through the inertial navigation system. So this is actually a pretty interesting area where we will be getting the rotational roll pitch angles of like angular movement of the vehicle and translation how much distance it has moved through inertial navigation system we can capture. And pilot will be sitting in the ship and he will be controlling the ROV. And coming to the AUV, it is a closed loop system because it is autonomous vehicle. So these are all the parameters we have to give heading controller, depth controller based on the environment. Environment means like depth sensor, everything will be there. So based on the feedback, your control law will change and then it will actuate accordingly. Okay. Control allocator means which thrusters I should make, which pin I have to control. So this is like a PID loop and this will be controlling the AAP. Again, sensors will be taken as a feedback and it will be according to the mission objective, it will be running. I will show how we have done. Coming to the hydrostatic in the man submersible, see general arrangement. How your components are all arranged in the vehicle. Heavy weight systems will be down, and all communication system payload should be top because we will have to communicate with the ship. So in this way, arrangement will be done, and the hydrostatic studies is actually given to IIT Madras, where they will be working on the scale down model. And the design also, when you come to man submersible, it should be designed like all our products will be certified by ISI like that. We are having international association certification standards. So they will be certifying our design and then only we can go for realization. So this is the hydrodynamics propulsion system for man submersible. These are all the BLDC clusters. BLDC clusters, and this is the scale down model. how much speed power is required to maintain that speed. That parameters and all will be deriving. So power systems. When you come to power systems, see here, this is the 7,000 meter cable where this is the vehicle, remotely operable vehicle. And here all the containers will be there. So when you give the voltage, required voltage from the ship, it should go up to 6,000 meter depth. So we have to increase the frequency to reduce the transformer size. So that and all has been done. So what is the optimized frequency? That is 400 Hz. At 400 Hz, we will be transmitting the power for the remotely operable submersible from the ship. And I was telling no for autonomous vehicle how you will be computing the battery size. So first energy budget estimation. So you know how to know the concept of operations from the deployment of the vehicle. What operations you will do, how many sensors you will power on, how much it will come, like what is your vehicle duration, and how much is the coverage surface area. Everything counting, we will be doing the sizing of the battery. So if you see for the AEB, we are using the lithium ion battery. Two packs will be there, main and redundant. Like this for Matsya vehicle also, we have realized that the pressure compensated batteries, which are certified by DNV actually. So this vehicle duration of the Matsya is 12 hours, but emergency 96 hours. So total 108 hours it has to take. It has to compensate for all the operations. Like that, this also is for around 55 hours. So coming to navigation and positioning, where navigation is playing important role. So here, if you see the mission planning, so from one point to one point, I have to go. At the time, the vehicle should decide the optimal path. Come path planning. So then it will set the control points, set points, and it will give the control system. Then the control system will dispense what is the speed, or how much RPM the vehicle should thrusters should run. So after that, again sensors will take, and we will be sensing what is the speed of the vehicle, and it will give the feedback through the navigation system. Where from the navigation we will be getting the real time position of the vehicle. So whether so this is a closed loop. So from the real time navigation is continuous update of position, motion, speed, track, trajectory. These are all the parameters we need. But how we will know the position? If you are in surface, we are having many satellite constellations to work. But in water, it is not so. Your electric like attenuation is more of the when your frequency is higher, the attenuation increases and they cannot penetrate. Okay, propagate. So we have to go for dead reckoning. So normally, very olden times, our sailors used to take big ropes and then they will measure from one point to one point and they will know the compass. Like North Star first they should see. They used to see. After that, magnetic compass has come. Then after that, like this dead reckoning procedure was invented. So we will be knowing from what which position to which position we will move and what at what angle. So at that time we will be knowing the how much we have moved and how much we are away from the actual trajectory. This is called as a trajectory. So we will be getting heading with the normally compass or gyro compass, and displacement will be coming from the accelerometer or velocimeter in underwater. So are these two parameters enough to compute? But okay, not accurately, but it's okay. So we need the velocity, but we will be knowing. So our vehicle is moving. So this is called as a body frame. So it will know it's only local frame. But when you are in Earth, we should tell in the latitude longitude. Then it's called as a navigation frame. So we have to convert this to this. So at the time we need roll pitch yaw. These are called as Euler angles. This is called as a direct cosine matrix. So we will be converting from body frame to LED frame for the position determination and how we are determining. So initial latitude longitude will be knowing from the GPS, and when vehicle goes in water we will be getting the velocity of the vehicle through Doppler velocity law, and then we will be getting the angular moment of the vehicle through gyroscope, and we will be using these formulas to get the next position. These are all the parameters which are all constant. because we cannot change so easily. They can contact me to work on this. So this is a navigation algorithm, whichever I explained. This is explained here. So this is the inertial measurement unit, which is consisting of accelerometers and gyroscope, and vehicle will measure its own velocity in the body frame. When you are converting into navigation frame, this navigation equation is used, and then we will be getting the position in the navigation frame. Then Kalman filter. Why Kalman filter is required? Why inertial sensors are required? Because inertial sensors normally has its own scale factor and bias, where normally when you see from accelerometer, if you want to get the position, you have to integrate. You have to integrate the acceleration to get the velocity and integrate the velocity to get the position. So at the time constant, two times here it is added. So it is having its own drift. To compensate that, we are having the Doppler velocity law. So Doppler velocity, in the last talk also he was telling the current profiler. This is can be used as a current profiler also, where it will measure the velocity of the underwater vehicle with respect to seabed. So it will emit the four acoustic pulses, and then it will transmit the ping, and it will get reflected. So the frequency shift is there. Here if you see the time difference is different, and here if you see the time difference is different. So the frequency shift will be used for calculating the velocity using this formula actually. But when you are in the first initially when you are in the sea surface, you will be going. So this is the sea current which we have derived from the ADCP, from ADCP sensor, and we have measured the sea current profile up to 5,500 meter depth, and this we have been using. But your DVL will also measure the sea current and also the vehicle velocity. So we should add this input velocity and the sea current velocity, and this is a sensor error model where we can generate the data for your whatever velocity, and then we can see how much position deviation is there. According to the mission objective, it will be running. I will show how. Gyroscope is, I was telling, no, for the angular movement of the vehicle, how we will detect the angular movement. It is called as a gyroscope, where normally we will be using the angular rotation movement like a roll, pitch, heading. How to sense it? That is through gyroscope. Initially, we were having the mechanical gyroscopes which were used in satellites. When I was working in ISRO, mechanical dynamically tuned gyroscopes were used. So now it is compensated. It's very big size. It will occupies more space in your vehicle. So when with the time and with the technology development, we have gone for ring laser gyroscopes and fiber optic gyroscope. Now MEMS gyroscope. Your all phones and all gyroscope will be there. MEMS gyroscope. Then only we are changing the orientation of your phone, horizontal, vertical. That is sensed by the gyroscope only. How this gyroscope principle works, how you will detect. Here, if you see, this is a fiber optic coil. This is of length 1 kilometer. This is a bound actually, and then here one light will be transmitted, and the opposite also one more light signal will be transmitted, and with your vehicle movement they will be colliding, and that angular shift will be measured as the angle. So we have done actually one modeling tool for sensor selection. So based on your application, you can select what is accuracy you require for the gyroscope, what is accuracy we require for the accelerometer. So I have carried out for three grades, and for this which scale factor bias and angular random walk will be very important. So based on that, if you go for with the type A, type A means we will get 30-meter error. If you go with the type B, 90-meter error. So selection of sensor also is very important when you are working on the navigation sensor selection. So normally this is the concept. Navigation scheme. This is the initial navigation system. First, initially it will be aided with GPS, and once it goes into water, we will not get the GPS signal. At the time, we have to depend on the Doppler velocity log and that sensor, and also aided with acoustic positioning system. But acoustic positioning system, how efficient it is? And why we need inertial navigation system? As I told, the acoustic positioning system will have its own delay because at 6,000 meters, when you want to get the signal from transmitted from the ship and then it comes to back, means it will take 8 seconds. So during that time, what is your vehicle? It would have shifted. But whether the shift, whether we can measure that, that's why we need inertial navigation system to have a continuous update of the position of the vehicle. So if you see here, this here our this USBL transceiver which is mounted in our ship, and this is the vehicle where our transponder will be mounted. They both will communicate and they will be getting the position, and these are all the equations we are using. So it will be searching the position of searching the vehicle transponder. It's called as a beamforming technique, and which is already embedded in a positioning system. So we are having like a three positioning systems. So normally in GPS, if you see how your position on the Earth will be computed, it is like a triangulation principle. In the same way, we are also having in underwater. This is called as underwater GPS. You can tell. So if you want to have a very accurate position in centimeters, we will go for long baseline. Baseline is the distance between the two transponders is called as a baseline. How long we keep and how many we keep that matters. So this is called as a short baseline position, and this is called ultra short baseline. And we will be using this one only because here multiple array of transducers will be mounted in a very like small spherical hull, and we will be getting a accurate range and bearing angle of vehicle. So these are all the methodologies, techniques we use. Uh, Velocity of sound is very important. I was telling 8 seconds, it will take at 6,000 meter depth. That is the velocity. Velocity is 1500 meters per second. Velocity of sound in air is around 300 meters per second, but in water it is 5 more. But it will not be uniform when as per the depth because it depends on the salinity, pressure, and temperature. So salinity, how it varies. So in this formula, we have to incorporate and we have to get the current velocity of sound. So it depends on the depth, temperature, and salinity. So now if you see the sound velocity profile will be like this. It is called as a thermocline region where temperature decreases rapidly. So your sound velocity also is reducing 1480. Again, when you go into deep water, it will increase. In this way, so many challenges are there. So coming to communication, communication also. If you see acoustics, we can go in communication in kilometers, but bandwidth is very less, and multi-path propagation we have, and noise also will be more. Ambient noise also we have to encounter. So optical, but optical scattering will be there, and we have to be in line of sight, but range will be in hundreds of meters. If we go for electromagnetic, that also will be like, but you have to have a very big size of the electromagnetic supply. Then if you go for radio, it cannot go less than 10 meters, and that also depends on your frequency, operating frequency. If you go for less frequency, at least you can reach to 10 meters. Only we can go with acoustics, and based on your range requirement, you can select whichever need comes. Normally, acoustic communication, how when they have like during Second World War, this underwater telephone was like made with analog single sideband modulation, but now spread spectrum modulation techniques are used and data telemetry, everything has come. So from 2000, we are using many like advanced modulation techniques in communication. And recently, I will show you in our non-submersible acoustic data telemetry worked very well. But spectrum modulation and digital modulation, so we don't have any challenges. So propagation of sound with sound velocity profile. So if you want to see the sound propagation, how it travels, so we should have the input sound velocity profile. If you see this 1,000 meter, 1,000 meter range, here itself it is reflecting. But when you go into down water, here many surface reflections are there. But when you go in deeper water, your rays are reduced. When you go in deeper water, your reflections based on your soil bed properties and all, it will vary. So even sound velocity profile, sound velocity varies with seasons and like location also. Our Indian Ocean profile will not match with Pacific Ocean. Okay. So now we are working, we are trying to understand the acoustic channel propagation in shallow waters and deep waters during ray tracing methodology. And here Bellhop technique also is the Bellhop where we are having libraries and now I'm working in Python. So where we will be taking from the sound velocity profile with the temperature and then we will be giving the where your transmission is there, where your reception is there. Then we will be working on the beam density analysis to get the transmission loss. So here, this is the different sound velocity profile and how your propagation will. Just I wanted to show. So these are all the equations which where the transmission loss. So we are having the mathematical models and the empirical formula. But empirical formula will get as a constant. But when you see the like Bell model and all, then we can see how it is propagating, how much your beam density is varying. Again, when it is regenerating. So many parameters I'm understanding. So this is the transmission loss in deep water, shallow water, how it is coming. This is the noise level. So here, these are the sonar equations where we will be using. And based on your range requirement, bandwidth requirement, you can select. So here, this is acoustic positioning. So always our underwater vehicle, we have to follow, ship should follow because we will be in 12-kilometer range only for operation. So that's why I wanted to show this one. In those we are having the navigation scheme we are following. And I already explained this one. We have this INS which is mounted in the vehicle. And then this is actually, we have used satellite communication to stream all our underwater images to surface. So this is actually when they joined using Inmarsat satellite and Link broadband, we have realized this is the shallow water ROV. This is a 500-meter depth rated. Here we have developed indigenous navigation algorithm to estimate the position of the vehicle because we cannot accommodate this photonic inertial navigation system because it is very costly and it needs so much space. So indigenously we have developed and we have found that it is less than 5% of the position error. So these are all the visuals which we have collected in Antarctica. And when you go into polar region, we have to go with inverted deviate configuration because we don't know how much depth is in polar. So we will be taking the reflection from the surface of the ice. So at the time, your positioning technique will be different actually. So if this is our AUV, which I was explaining, which is having endurance of 48 hours and communication payloads and all will be on the surface. Then inertial navigation system is there and we have to be in the operational beam angle. If you are here, it is very optimal. But when you are away from the ship, we will be ready the quality of the signal and we will get the very good. So this is not very important. So this one actually A32 aircraft which was missing in 2017 and then we recently went in 2023 and these are the mission plan we have and AUV was making the trajectories and we were collecting all the pictures. So this is the missing aircraft we have collected and we have given to Indian Air Force. So I was part of that cruise action. So this is coming to Matsya vehicle. So this is our master machine which we are, I was telling. So the concept of operation. Showing the video of the Hawking, right? So where how we set the inertial navigation system using our sensor error model. So many redundancies techniques and all we use. This is the navigation architecture. So in remotely operated vehicle and all we are having only one system, but here we will be having redundant acoustic positioning system. Accordingly, we will be using all the transponders and the position will be coming in the mission control center in the ship. And these are the various devices, navigation, positioning, and communication. And this is the PDM modem. When your Massa surfaces will be getting the position through the Iridium satellite actually. Iridium has more coverage than other satellites. So recovery challenges. If no navigation sensor is working, where it will surface. That challenge I have taken and I have computed the position and I will explain it. Then this is acoustic data communication where we have tested at 25-meter depth in Bay of Bengal. And then this is the schema we are following. We cannot send like 1,000 bytes like your Wi-Fi communication and all. Here we are having limitation on the data bytes. 48 bytes each and every frame. 64 bytes we can send. So 64 bytes with 512 bits. So we have divided all the parameters into 50 bytes the chunk of data. And then one by one, we will be sending every 10 seconds like that. And the OEM is claiming 6.9 kbps, but we have seen only 1.6 kbps at 6,000 meter depth. So this is the software which we have developed for the acoustic for Massa 6000. And during when all the objectives. So when you develop a system, you cannot just go for a deeper water and test. So first, your whatever design you have done, power system, control system, whether they are working or not, flotation, vehicle is floating or not, then full submersions when during with your ballast mechanism, whether vehicle is going inside the water, and then life support because it is a manned submersible. We should have a life support where the man will be the 1 atmosphere pressure hull. But we have to provide all the oxygen support, carbon dioxide scrubbers and all. So then surface maneuvering and thrusters enabled diving also we have done. So this is the flotation. I was explaining the stability and all. So these are all the methodologies, inclination, flotation tests were carried out. So here we are varying the sizes, dead weights, and we are balancing the vehicle and we are seeing the tail. How much, as per our design, is matching or not. So diving the vehicle around 40 meters, the vehicle was driving for forward motion using our joystick. So how much our thrust, whatever model, the power required is sufficient or not, we have checked. So this is the communication I was telling. This acoustic communication, our acoustic telephone at 6 meter depth it did not perform well. So even surface communication with VHF, then just at the time we have mounted the VHF inverted and then we were in the line of sight and the communication was working and then we proceeded for the man race. So underwater vision systems, when you come based on your like illuminated area, we have to capture the image. So that also matters. If you see in our AUV, we have the cathodic camera and the light beam should be this much steady. So that is one software is there where we can study and on modeling only slides and cameras were placed. Because without light, if your camera is seeing, it will be like a dark only. So that is based it's not a valid design. So this also plays important role. Locomotion, I was telling like clock based how much force is required. So these are all the parameters we have to take when we are designing the locomotion based vehicles. So some demanding needs. See, the Malaysian aircraft was missing, and how many ROVs were deployed, and so many like Dawn aircraft was missing. Now AN-32 also was missing. Till 2023, we were not knowing it was missing only, but no footages were there. So we need many vehicles for this type of challenges also. And recently, this